we are going to talk about robotics and even like going into layers into robotics more technically now. So I'm Guillaume. I'm a software engineer by trade. Like I started as a software engineer, but I have the past, let's say, decade in my career. I've been in robotics, helping roboticists to actually put the algorithms into like self-driving cars or like drones and so on. And yeah, I learned a lot from that experience. Along the years, right, we built middleware for robots. Right? You probably know the middleware called ROS. And but when I remember, like even 10 years ago, right, I was going to a company, ROS was there, right, and my boss, right, told me like, do not use ROS, make something better. I was like, maybe. The thing was really hard. Like you were building, even if you had like a ton of budget and so on, you were basically building a robot and building the tool to build the software for the robot, basically, like the layer in the middle. But when, for example, at Agoya, right, I built a middleware, I came back to the same mistake as ROS did. And let me give you a little bit of background because you are probably familiar with this product. So that gives you like a reference point into where I'm coming from. Right? So ROS, in terms of like flexibility and in terms of talking to a roboticist, is pretty good, right? You have components. Let's say you have a motion planner, you have motion control, you have some computer vision or accelerators for AI. And you plug them and you basically have messages in between those tasks. It's nice, like you have a large team, you can have like somebody working on one component, you work on the other, you agree on whatever messages you send through, and it should work, right? The thing is, when ROS came to life, I think there was a kind of like, it was the height of the web services and the microservices, right? And they didn't know. I mean, even if you ask them, like the creators of ROS I'm talking about, you ask them from the Willow Garage, the company where it was created, they tell you we didn't know, right? We were kind of new grads, and we just did the thing, right? We internship, we did it, right? So they did something that was purely asynchronous, meaning that every single event in your robot just comes into something that runs in parallel into your system. Sounds cool, right? Like you basically leverage your parallelism of your computer, everything is independent, perfect, right? The thing is, like when you do that, is when you try to record what you have been doing in ROS batch, right? And when you try to actually replay them, you have what we call a non-determinism in the loop. Basically, you record like you're like, oh, finally this stupid robot just hit a tree. I want to have that on my computer, replay it, and fix that bug, and sometimes you cannot. Sometimes you replay it and it actually works. And so it's terrible because that does give like a kind of a cascade of consequences. Let's say like the safety guy comes in and say, yeah, prove me that what you do in simulation is actually what happens in the real world. You're done. You cannot. It's non-determinism. You haven't proven any link between what you are testing and what is happening. And as a developer also, it happened to me at Agoya, for example, we had thousands of tests because, yeah, we wanted to have robots in very complex environments where, yeah, you need to accumulate a lot of experience for your robot and a lot of unit tests or like kind of case tests like real world test cases. And you execute once and 2 fails, and you execute again and 15 fails. So you have no idea what you're doing. That, added to that, of course, it's a C++ first product. And C++ has a long history of issues. You're a roboticist, right? Most of you, right? You know that you have something else to actually do than actually looking at the intricacy of the little, like undefined behaviors that the C++ compiler doesn't tell you at all, right? You do something, you reference like a reference on the vector, and you keep adding another element. You just did an undefined behavior. Nobody tell you, right? So that's also something that I live, right? Like trying to support like roboticists, where they were like, well, it crashes, it's probably the NVIDIA driver. What? No, right? It's not, right? It's your code. Yeah, I know it sounds like innocent, but it's really bad. The performance is terrible. We see that, and also in terms of practice, you probably noticed that it's really linked to your environment. So basically, you're married to other point with ROS. So all in all, like you see that it's good to experiment, to do something on the corner, but when you try to scale, when you try to build a company and try to actually put products on the real world, that is actually working a lot against you. So this is why I built Copper. So Copper is a Rust first SDK on runtime for robots. So it's really more than just a middleware. Right? It gives you not only login, but also it creates for you an actual runtime. So we'll see how it works. What inspired me to actually build Copper is what happened in the gaming industry. And when you look at it, there are a lot of things that you can actually translate from what I did with Copper with the gaming industry. I don't know, some people maybe have some gray hairs like me remember that, yeah, back then in the day when you were building a game, it was like me at Argo AI. We were building actually the infrastructure to build the game as we go, like the rotographical things they did in Prince of Persia at the beginning. The guy did the tool by themselves when they were making the game. Until Doom arrived, that was the middle one, like in the 90s. And everybody talked about Doom, right? Like, why Doom? Because that was the first time somebody thought about, like, let's make an engine to build games. So basically a tool in the middle to actually accelerate your development and make your time to production, right? Like as short as possible and as reliable as possible. And look at where we are today, right? You know, for example, for a robot, you need to actually have a lot of people around the table that don't even speak the same language. Somebody's going to be like a photonic engineer making like a sensor, and the other one like a mechanical engineer going to like, I don't know, tolerances for a camera, stereo camera. The other one's going to be a networking engineer saying like, why you have a contention in your robot. So you see a lot of people with a lot of specialties, well, I'm not even talking about ML and so on, working on the same project. Look at where the game engines are today. You have 3D graphics engineers, or like creators, sorry, creating like, I don't know, those little characters. You have sound engineers, like movie script creators and so on and so on, all working on the same tool. That's the vision of Copper. So, that is really beautiful. Let me see that. So one thing, oh, sorry, that's not what I want to do. So one thing, when you look at ROS, it works like that. You have your components, and like you have like events coming in and coming out, and actually waking up your system. With Copper, we will transform this DAG into something that is completely linear, right? And it's going to be one loop. Again, think about the game. Again, you have a game loop. A game never does something asynchronous. It always actually loop over, the same loop. And that makes the thing very reliable and very reproducible, right? Even if you have like a bunch of events coming in. How we do that, right? Instead of like figuring out what is basically the scheduling at runtime, like ROS, we do that at compile time, right when you compile your ROS code with your tasks. How do we do that? It's some kind of magic, right? We have some what we call like metaprogramming with Rust. It does exist with C++. It's way easier actually in Rust. And we do figure it out, like while it's that kind of an extension of the compiler. It gets your DAG, your list of tasks, and try to guess, okay, how should I schedule your task and build that loop? We really like literally build a game loop out of it. The goal then, it's not done yet, that's going to be the vision so you can see a bit where it's going. It's going to be to do that with round trips. So basically you compile your schedule, you deploy your schedule on your real hardware, and we will be able to get metrics of your robot and adapt the scheduling at compile time for your next compilation. So you can imagine people kind of improving the performance of their robot as they go, and even if they add a new task, it will auto-tune the robot. Imagine, for people like me that has been tuning like robots forever, that's actually a marvelous thing if that works. So all in all, right, like when we build Copper, what did we gain? So determinism, like literally you run your code with Copper, you wipe out the outputs from the log, you replay the same log, and then you compare binary of the two logs, not one bit's gonna be different. That's how I test determinism. The second one is designed for safety. So that's the end goal of all this, right? Like when you have a deterministic system, you can actually prove that what you generate is actually what you get. And like safety certified compilers, Copper is basically a compiler from what I explained to you. So when you certify a compiler, basically Copper could be also seen as a high-level robot compiler that can be certified for safety. It's really performant. I mean, I'm so ashamed that I don't even publish the numbers. Like the latency can be like 100x less than ROS. If you build like a project with default ROS, I think there are just own examples and I just compare. The logging, because everything is linear with Copper, with their SQLite version, which is the default again, we are 12,000 times faster than ROS. And okay, they realized it was really crappy, so they fixed that. This new thing called MCAP, we are 12 times faster. Right? So you see, when you are thinking about like very at the first principle on a topic from end to end, you get those kind of results. So what does it mean for you as a roboticist? Okay, cool, it's performance, so what? I don't care, maybe I have enough compute in my robot. It means that you are not afraid to actually split your stack into like way smaller little elements, so you can test them better, right? So again, it goes into your production thing. You can have like a lot of little elements because it's basically free to actually have them log and have them run. And again, like tune your system as you already iterate on, like I was saying. Are you ready for some code to see how it looks like? So that's how I define this graph of tasks. You define basically an ID and you give the type that just implement an interface or create in Rust. That's how you basically tell Copper, okay, get those pieces of code to actually that represent tasks in the system. And you can give them a config, for example, you have a little thing there, the tool config, and you have like also generic like elements, like I don't know what rate you want to run your robot, those kind of things. And then what you do, that's in the same file, but I split it into because it's a long one. On the right hand side, you connect basically those tasks to one another. So it's very easy, like in terms of what you do, and you precise like, okay, what is the type of the message you want to send from the one to the other. And then, okay, cool. So that you made a kind of your overall DAG. Now, in details, how you develop that. Okay, so you basically this complement a trait. Like if you don't know how to read Rust, it's fine. That's like an interface in C++. That prescribes like a list of methods basically you need to implement. And one is just process. This one is a source task. So a source task is basically like a driver, basically a source in your system of information or messages coming in. And what you need to implement is basically, I give you a clock, so the robot clock. So yeah, I will not give you like a lesson in terms of how timing is important with robots. That's actually a global clock that you can synchronize on. And an output, which is a mutable type that is defined there, right? Like you remember which one we use in the DAG, that's this one. So that is very prescribed. Like your ID basically generates everything because it's just an interface to implement. And then you don't have to. So Rust, you probably heard about like the borrow checker. I did that because like when you present that thing on a small component for roboticists, they can just use those predefined input and output, and they won't have to find the borrow checker at the beginning, especially at the beginning of the adoption of their project, right? And later on, they could get used to it, but at least at the beginning. So So yeah, that's really something where it basically generates like as much as possible, so it's as easy as possible for roboticist that has something else to do than figuring out like thread processes and mutexes and so on. And guess what? It's just a normal Rust workflow. If you heard about Rust, everybody is like crazy, raving about like the Rust workflow. It's the same. It's just a project that I can actually show you like a little demo right after this. Okay, to kind of wrap that up. I was talking right at the beginning, so it's looked out of order, about this Rust for robotics. So Copper is part of a larger project. We really try to help the adoption of Rust in the robotics domain. And we do have like a workshop at ICRA that we did this year, we will do next year, that actually basically meet the academia, the startups in robotics, who are more applying robotics, and all those like creators for basically the ecosystem for Rust for robotics. And really, what I see Copper as, more than just like a runtime, is kind of a bridge to all those like amazing like crates. Crates are like libraries in Rust that has been created around in robotics. You probably already know a bunch of them, because even if you are using C++, those crates are so good that you are using them even if you don't know if you're using it in Rust. So one I can show, for example, so Fire and algebra are like linear algebra crates. Cordia is computer vision. Baby and Avians are like, that's what I use for like a little simulator, for example, for Copper. So like, it's like a game engine plus a physics engine. ROS ROS2, you know this one. Zeno, probably knows this one too. Rerun, who has used Rerun in a room? Not bad. So Rerun is really Rust first, right? Like, it's an amazing thing. Like, if you haven't tried it, I highly recommend Rerun. Like, it's a way to visualize your data very quickly in real time on your system. And because it's Rust, if you use Copper, 2 lines of code, boom, you have either your camera, your point clouds, or your synchronized data immediately. First love, I put some first love here, which is kind of a competitor of Rerun somewhat. They are also actually Rust first company. And a bunch of them are created every day. I learned actually on another one today. You want a quick demo to see how it looks? Much time? So can we make a prayer for the gods of the demo for me? Big. Look at what I'm doing. Cargo, run. Cargo is just like the compiler for Rust, just running my thing. So that's a complete project that is running in Baby with actually the physics engine too. And if you look at let me see that. If you look at how it looks like, right? That's basically a little. Sorry, it's hard to do like 2 things at a time. It's a little like self-balancing robot. Right? You can actually look at it. This thing exists in real life. It's in my office. But you can interact with it. Like if you want to touch it, if I can do that, to interact. Okay, I can. I need a little bit too much. Resetting the demonstration. So you see, it's kind of a very simple example. So for roboticists, it's like, it's kind of a stupid robot, but that's the point. I don't want to explain the robot, I want to explain Copper. So Copper, you have still, right, like even if it is one big loop, you still have this notion of like a tree that you can see running. You have some little feedback actually coming in, so you see basically the PIDs, like your roboticist, you know what it is, right, that are actually giving their feedback, so if it is good. On the left-hand side, you have like the two inputs, which is basically the encoder for the position of the rail, and the other one the angle for the stick. 2 PIDs, and then merge those PIDs. So those are regular tasks, right? They are input and outputs. And here, like when I'm merging bits, so basically I'm making the mix of the two. So not only I center the robot, but also I make it like stay up. And then you have on the right hand side basically an actual motor, like it's a stepper motor on the right hand side for the robot. And you see how much like Newton it applies to the thing. So yeah, you need to always translate like for the simulator what is the real model of your actuator to your real motor. Right? So yeah, that's copper in a nutshell. So if you like what I'm doing, like that would make make my world if you start a repo. We are at, I think, like 850 stars. Guys, we can make it to 1,000. And yeah, do you have any questions?
What was the first one?
Yeah, thank you for the talk. And my question is related to what's the licensing of copper? Is it just free or is it special licensing behind it?
Do you have a lawyer? No, it's just
no, but
I
just had some experience with.
It's just an Apache 2 license, so it's free forever for the core.
Check.
No, okay. Kind of two questions. First one is, are there any real-world industrial deployments of this yet that you know about?
Yeah, so my first customer is in the self-driving trucks. So it's a French company. It's not in production yet. They are porting their stack from the top, from like the sensor fusion and so on, where they do have like a bunch of like issues with ROS in terms of like performance and so on. They are going down the stack. They have been actually contributing a lot of code to for example, the copper to ROS bridge. That's them that they needed to port a stack by it. I have also another project moving on it's a DARPA project with drones, pretty cool one, and another one is more like academic also it's I don't know, little lunar rovers. So that's another one. So, and I think somebody is porting it for like a submarine. So I have almost all the mediums, at least like air, ground, space, and water.
And then the second one, I mean, you talked a lot about all of the positive games, which is amazing, dealing with ROS personally as well. Are there any trade-offs with using copper-ROS over ROS?
So one's going to be the ecosystem. This is why you see me too. We need more of us, right? Like to contribute port systems and so on. And one of the number one thing I hear about copper is like, yeah, cool, I have a linear algebra, great, but give me a motion panel. It's not done yet in the universe, right? So, but it's moving, right? Like you would be talking like 5 years ago, we would not have all those like low-level crates, and all those crates you will be able to build those kind of higher level things. One example that got fixed, for example, is like somebody wanted to make like a more complex robots with articulations and so on. So they needed transform trees with copper. We implemented that pretty quickly. Now it's actually a compiled time now. Initially it was like ROS at runtime, and it's compiled time. So it's coming, and those crates, even if they are coming from notions that were in ROS, for example, the TF was from ROS. You see that we copperize it, right? We do allocations and so on. So that also improved this ecosystem. But yeah, again, that's going to be the thing. The ecosystem is okay. Yeah.
Okay. And you mentioned determinism. And aren't some problems like fundamentally asynchronous? For example, different sensors coming at different rates. How do you deal with that?
Yeah. So determinism is between when your stack basically realize that the data is there, to how they record it and how they used it at that point, and how they will reuse it from the recording side. So, for example, if you have something like, let's say, an IMU, right, 1,000 Hertz, you cannot run Copper at 1,000 Hertz. So you can actually basically either like compress the signal or buffer it, or you have the choice of doing. You have actually like helpful things in Copper actually to do that, like aligning and compressing a lot of data, to actually adapt that to the pace of your global pace of your robot, if you would like. And that doesn't change the determinism. Right? You basically switch from an asynchronous world, bridged from an asynchronous world to a synchronous world. Think about it, like how a game, you have thousands of players on, let's say, Valorant, right? Or those thousands, like 10 players, because it's only 5 versus 5, right? How do you know, like everybody is actually playing on it, everything is an event? No, they just buffer it, reconcile that at a loop level, and everybody, including the remote players, are actually playing at the same level on the same loop. Right? That's the same concept.
You mentioned that you flatten the acyclic graph when you realize it, but like the point of having it like in the different processes, that if one of the branches is stuck, you still have the other that is floating, like flowing the events. Of course, it's not like often the case, and everything is still stuck, but it allows you to build like a tree or like a graph that if one of the branches is stuck, you still can process like a signal. So how you deal with when you linearize it? For example, like one of your blocks stuck.
Very good question, right? So we introduced actually background tasks recently, where okay, you go through the loop. The first time around, let's say you have a very long CV or AI task, so you don't want that to block your 1,000 Hertz IMU, right? So you spin that up. It knows that at that cycle, it's called a copper list, it started, and then it's like this thing has been basically dormant and non-executing until it gives the result at another copper list, right? So that jump is actually also deterministic, right? Like when you replay it, it will actually re-give the data in the future, right? On the correct cycle in the future. So that's going to be one. Another thing I started to implement, but don't yet know, is to basically make looping possible in the scheduling, which is like a more pure way of doing it, knowing that basically learning that, oh wait, this thing is one execution, it's going to be stuck, and I can do like around 1,000 of other things, like on like a sub loops before actually can come back to the first one. It's not done yet, but like the background thing works well for now.
Thank you for such interesting presentation, Leona. My question is, when we, in this all new great world of transformer neural network with humanoid robotics, how it can work with a lot of Python code that should run on this network with all this, like, not very good deterministic behavior and so on.
So that's a good question. So you open a little kind of worm into the inference determinism. We can talk about that offline. But for example, Copper, like when you have like those tasks pushing messages from one to another, do support